This is chapter 17 star stuff. Still continuing on with astronomy here. This is our star unit. So basically, again, another short chapter. So I'm going to talk about life as a low mass star, life as a high mass star, and then the roles of mass and mass exchange. So first off, how does a star's mass affect nuclear fusion? So we've talked about this yesterday a little bit in our lecture, but the mass of a main sequence does determine its core pressure and temperature. So if you have high mass, it means you're going to have higher core temperature and more rapid fusion. Therefore, these stars will be brighter or luminous and shorter lived. If they have a lower mass, they'll have a cooler core, slower fusion rates, and they just have smaller luminosities and a longer lifetime. So, HR diagram showing the lifespan of stars. Now, stars are found in star clusters. Okay, and our knowledge of stars comes from mathematical models as well as observations we've made. And just know that star clusters do contain stars of different mass that were born about the same time. So they make great specimens to study. Now, life as a low mass star is not that exciting compared to a high mass star, but we're going to talk about protostars where it enters into a main sequence, and then once it uses up all of its hydrogen, it might become a red giant star. And then we'll talk about how it burns helium instead of hydrogen, and we get this double shell burn-in of it, where it basically turns into a planetary nebula and then ends up as a white dwarf. So a star remains on the main sequence as long as it can fuse hydrogen to helium, and we know this, that stars, once they start to lose or burn or fuse all of their hydrogen, they become larger, redder, and more luminous when their time in the main sequence is over. So our sun will eventually become a subgiant to a red giant in its lifetime. Now, red giants are broken thermostats. Remember that there's a solar thermostat that controls like the rate of fusion based on a few variables. So as the core contracts, hydrogen will fuse to helium in a shell around the core. Okay, so we have this hydrogen core fusion going on here, but then luminosity will increase when the core thermostat's broken because our fusion rate will increase. The shell does not stop the core from contracting, so it starts to expand. Helium fusion does not begin right away because you need a lot of high temperature for that to occur, but then once it does occur, that's going to expand even more, and it will take place in a different part or a different shell, if you will. So we call this a helium flash. Okay, so now instead of hydrogen fusing in the center, we have helium fusing in the center, and there might be still some hydrogen fusing out here, but remember our thermostat's going to be broken now. So we have core temperatures that rise rapidly, fusion skyrockets, and as a result, it's not going to shrink nor grow until it's kind of temporarily fixed when it's in this little helium flash stage. Now, after the helium flash, it should shrink and become less luminous, but our observations, basically agree with those. And so we kind of have this horizontal arm in our HR diagram, or horizontal branch, that shows helium burn-in stars. So how does a low mass star die? So helium fusion will stop, and then we get this double shell burn-in that never reaches equilibrium. It spikes upward in a series of thermal pulses, in which each spike we have convection that dredges up carbon from the core and transports it to the surface. And then eventually it becomes a planetary nebula, where the double shell burn-in will end. It ejects hydrogen and helium into space. It's not a supernova, okay, not as explosive, but the core that's left behind is your white dwarf. And then finally we get the end of fusion. Core temperature is not hot enough for fusion to take place of the heavier elements that are still there, and so then we get a white dwarf. So life track of a sun-like star like ours, we have the sun, becomes a subgiant. Here, if you take a look at the core of it, inert helium, hydrogen fusion on the outside, but then it can spike into a red giant and come back down. Here's that horizontal branch to the double shell fusion of the red giant to the planetary nebula, and that's going to circle back down to a white dwarf. Now, Earth's fate when this occurs, sun's luminosity is going to increase 100 times its current level, which is way too hot for us. Not only that, the sun's radius is going to grow, and it's going to basically grow to the size of our orbit, so it might engulf us. Now, life as a high mass star is a little bit more exciting, but we start off with a protostar to the main sequence star to a red supergiant, and then it's going to have helium burning supergiant to shell burning supergiant, and then finally that explosive supernova, and we're going to be left with a neutron star, not a white dwarf. So I want to talk a little bit about this carbon, nitrogen, oxygen cycle, where high mass stars fuse hydrogen to helium at a higher rate, using these heavier elements as catalysts, and as a result, our core temperature is greater, and it can overcome the repulsive forces of this. So the life stages of a high mass star, very similar to low mass stars. We still get hydrogen core fusions, especially in the main sequence. We still get hydrogen shell burning when it's a supergiant, as well as helium core fusion. Now, high mass stars are responsible for a lot of the heavier elements in the universe, especially those found on planet Earth. We're talking oxygen, neon, magnesium, iron, uranium, all of these heavier elements that are found in our periodic table. So the Big Bang, when it happened, mostly made hydrogen and helium, but stars have made everything else on the periodic table. Silicon, sulfur, calcium, and iron, all of these were made by high mass stars. Okay, with high mass stars, we get multiple shells burning, whereas with low mass stars, there was like one or two. So here we have multiple, and you can kind of see that we have in the center iron fusion, silicon fusion, oxygen, neon, magnesium, then carbon and hydrogen and helium and all of that. But once it starts to do iron's kind of the dead end of it, and that's kind of like the end of the lifespan of this high mass star. Where was I going with this one? Oh, this is a graph just showing the relative abundance of these elements, and as we get heavier, the abundance of them does decrease. So hydrogen and helium are very abundant, but the heavier elements are less abundant, but they are still there. So how does a high mass star die? Iron's going to build up in the core. It can no longer resist gravity. The core is going to collapse, and that's where you get your supernova explosion. Neutrons collapse to center, forming a neutron star, which is very, very dense. And then as the supernova occurs, elements heavier than iron tend to form. We get gold and uranium, and it shoots out, and those stuff can be condensed and form a new star. So we are basically made up of star stuff. So the remnant of a supernova, these are some examples that we have seen in the lifetime. The Crab Nebula, pictured here, is a remnant of a supernova seen at AD 1054. The closest supernova in the last 4 centuries was seen in 1987 here. Zooming in on that picture. So the roles of mass and mass exchange, they're pretty important. So mass determines its life story. High mass stars, short lives, become supernovas. Low mass stars, long lives, never really become hot enough to fuse carbon and those heavy elements, end up as white dwarfs. Intermediate stars can make elements that are heavier than carbon, but they still end up as white dwarfs. So low mass star summary of its life cycle, we start off as a main sequence, we turn into a red giant, we get some helium core burn-in, double shell burn-in, and then we end up with a planetary nebula that turns into a white dwarf. And the reasons for this is the core shrinks and heats. It's hot enough for fusion, but then eventually the thermostat's going to be broken and fusion cannot occur anymore. Life stages of a high mass star, main sequence, we go into a red supergiant. Helium core burn-in to multiple shell burn-in where many elements fuse in the shells, and then finally a supernova, leaving behind a neutron star. Last thing I'm going to talk about is stars with companions. So remember, most stars in the universe are in binary systems, and sometimes they can transfer matter or flow from one subgiant into a main sequence star. So a star that is now a subgiant, that was originally more massive, can share or transfer its mass into a companion star, so we call this a mass exchange, and now the companion star is more massive and it can become a different type of star. Okay, so that concludes chapter 17, star stuff. Tomorrow's a work day. You're going to get like a packet of the lifespan of stars. It's not that hard. And then Thursday and Friday are Netflix video, basically the life and death of a star, which talks about a lot of the things we just covered, but obviously a little bit more relevant and way more exciting than me reading off of slides for you.